Okay, welcome to the afternoon session. So now we have Achilles Porphyriadis, that he's going to talk us about accidental symmetries near extreme black hole horizons. Please.
Thank you. All right. Hi, everybody. Thanks for the invitation. It's a great pleasure to be here. Right. So I'm going to tell you today about accidental symmetries near extreme black hole horizons, extreme and near extreme black hole horizons. So why do we care about extreme and near extreme black hole horizons? Well, they're observationally irrelevant. They seem to appear up there in the sky when the black holes are Kerr, and near extremality they are ADS2-like. But the prototypical example that everybody knows here is that the Bertotti-Robinson universe is ADS2 cross S2 is just the near horizon of extreme Reisner-Nordström. So most of the talk I will explain in this context, but we've done calculations that are now that now work for Kerr as well. So let me quickly remind you. You take the near horizon limit of those extreme and near extreme black holes. This ADS2 arises. Why? Well, it's actually a theorem in a very wide class of theories in many dimensions with minimal assumptions. And it basically consists of two things. The kinematics of saying that you have an extremal horizon implies that you have a scaling symmetry. But then the Einstein equation is the thing that adds and completes the algebra to SL2. And once SL2 arises, you have to have ADS2. So that's why this is so ubiquitous. But what I want you to take from this slide is that while these are approximations of the near horizon of extreme and near extreme black holes, they are also exact solutions of those equations, the same equations of motion. They're also exact solutions. So you could think about living in such a universe, let's say the Bertotti-Robinson universe, and asking about its perturbations. And it was already known back in the days from some of our most illustrious colleagues that back reaction in this type of context is kind of problematic. It's a bit strange and weird. And we can illustrate this from the gravitational point of view if we think about 4D gravitational physics as follows. So suppose you have a little bit of perturbation in this Bertotti-Robinson universe, for example. Let's say a scalar field phi, which you put on there, and you let it back react on the geometry. Is there a nonlinear completion of this situation to a nonlinear solution of Einstein-Maxwell scalar? And the answer is no, if you insist that this solution is still asymptotically ADS2. So the answer is no to that question, and that's what it meant, that ADS2 has to fragment, that there's no dynamics within asymptotically ADS2 spacetimes, etc. But of course, I mean, especially when we're talking about the black holes out there in the sky, something has to happen. If this is a near horizon approximation of an asymptotically flat region and there's a little bit of perturbation there, what happens? Back reaction somehow must make sense. And it does make sense when this ADS2 is actually connected to the asymptotically flat region. So if you consider the back reaction problem in asymptotically flat spacetimes, it does make sense, perfect sense. So this was realized, I guess, more recently, especially with the work in JT gravity. But of course, you would also like to make some calculations. And in this very nice paper, where they do some numerics, they actually study precisely this problem. They put in a scalar of order epsilon on extreme Reisner-Nordström in the near horizon region. And they nonlinearly find the endpoint of that. And they do indeed find what you would expect, that what this does is it perturbs the black hole a little bit away from extremality and produces a near extremal Reisner-Nordström with charge to mass ratio controlled by the size of that perturbation you put in. So if you do this problem in asymptotically flat spacetime, it does make perfect sense. So I want to quickly explain in this 4D type of language, how does the connection of ADS2 with another region outside help with this type of thing, and what are the correct boundary conditions, what's going on, etc. This formula?
Yeah. Instead of saying like that I have some amount of charge and I increase the mass.
No, don't read too deep into that. The reason I wrote it is because it's convenient to write it this way. I mean, all this is saying is that you start exactly extremal, you add a little bit of energy, it becomes near extremal by increasing the energy.
Right, but the mass is the same. So I would have increased the mass of the black hole.
I agree. I agree, but yeah, don't read too much into this. The difference between charge to mass, the only thing that this tells you is what power, what's the important power there. But yes, the difference is the thing that is the extra energy. Okay, so this is the charge to mass ratio of the final near extremal black hole, and it's epsilon the 1/2 away from being 1. Okay, so for this first part, I want to quickly introduce this concept of anabasis. For those of you who are not Greek or don't have a Greek origin, anabasis is a Greek word which means ascent to some kind of hill, some kind of low gravitational energy potential region, something like that. So ascending something. So this is the concept of anabasis, and I call anabasis the back reaction that destroys ADS2 boundary and builds this asymptotically flat region of extreme and near extreme black holes. This process of back reaction that destroys ADS2 boundary conditions is what I call anabasis. So let me review this real quick. So suppose you are such a Bertotti-Robinson observer. You live in this universe. The universe is asymptotically ADS2 cross S2. You study perturbations of it, and let's just study spherically symmetric perturbations of a magnetically charged version. So this is your background. You study spherically symmetric perturbations, and they are fully characterized by this gauge invariant quantity. Because it's spherical symmetry, this is not a propagating perturbation. All of the spherical symmetric perturbations are just 4 parameters, phi 0, A, B, and C. And they're all physical because this H theta theta component is gauge invariant. So what do these 4 parameters do? Well, you recognize what phi 0 does. It sets the scale of your universe. So if you change this m to m plus delta m, phi 0 measures this delta m difference. So you understand what that is. That's a parameter of your universe. What are the ABCs doing, though? The ABCs, let's collect them in this field phi. Let's call this solution phi. And let's see what they're doing. Well, they're breaking, first of all, they're breaking the SL2 isometries of your background. None of these solutions respects the SL2 isometries. So these SL2 transformations will rotate this ABC solution to another one. However, it will not rotate it completely arbitrarily. There is an invariant quantity, this SL2 invariant Casimir, a quadratic of ABCs, which has to stay invariant. So if you apply SL2 transformations, isometries of your background, you can rotate your ABC solutions around. And let's make a choice. Let's say that when mu is equal to 0, you're going to rotate away B and C and set the canonical solution to be A times R, let's say 2R here. And if mu is positive, let's say you're going to make the choice to rotate away A and C such that phi now is square root of mu times RT. All right. Notice that these SL2 breaking solutions, they're not asymptotical ADS2. They're growing linearly with R near ADS2 boundary. ADS2 boundary in these coordinates is at R equals infinity. So, U negative, I don't know how to interpret that. It might have something to do with having another asymptotic region, maybe wormholes, something like that. But that would require more study. Yeah, so I will assume that mu is positive or 0. All right. So why? Why there are these two cases? Because there are two ways to do anabasis of BR, of Bertotti-Robinson. So Bertotti-Robinson can arise from the near horizon of this Reisner-Nordstrom black hole of charge Q and mass M in 2 different ways. So the first way, the first limit here, is to set Q equal to M from the start and write the 1-parameter family of coordinate transformations like this, which puts the horizon at R equals to 0. But there is a parameter lambda in these coordinate transformations, which you then send to 0. Then there is a second limit, which you can do as follows. You can start with the Reisner-Nordstrom, which has this charge to mass ratio, so not exactly 0 initially. Do also a similar coordinate transformation, 1-parameter lambda, and send that to 0. So now the horizon is going to be map onto rho equal to 0. And these two yield the two different mu's. So in the first way of taking the limit, you will produce your Bertotti-Robinson universe at order 1, leading order, in Poincaré coordinates like here. And then by definition, if you look at what's the first order correction of this limit, you will produce one of those perturbative solutions of around Bertotti-Robinson. And what you get in terms of the theta-theta component is this 2R here. So what this tells you is that the 2R solution, which is the canonical version of any mu equal to 0 solution, up to SL2 transformations, is just a solution which I call a Poincaré anabasis solution, because what it does is if you think of the limit in the opposite direction, is it begins to build the asymptotic region of the exactly extreme Reisner-Nordstrom starting from Bertotti-Robinson. So the lesson is the nonlinear solution obtained from any mu equal to 0 perturbation of ADS2 cross S2 when you take into account back reaction fully in Einstein-Maxwell theory is an exactly extreme Horizon-Nordstrom black hole. How about the limit number 2? So limit number 2, if you do exactly the same exercise, but with the different charge to mass ratio to begin with and the different coordinates, at order 1, you get this. This is still Bertozzi-Robinson, but written in Rindler coordinates. And at order 1, you get a perturbative solution around this background here, which is given by this equation over here. So I'm saying this is still Bertozzi-Robinson, so let's put it back into Poincare coordinates, both it and the linear solution around it. And here's the transformation which will do it for you. So tau and rho goes to T and R. Here's a Penrose diagram. In TR coordinates cover the big wedge here. Tau rho coordinates cover the small wedge here. If you do this, the backgrounds go to each other. So now you have Poincare coordinates for the background. What does the perturbative solution from limit 2 map to? It maps to this minus 2 kappa times RT. So it maps to a positive mu solution. So limit number 2 produces an Anabasis solution, which you might call the Rindler Anabasis solution. And it's a positive mu solution. So we learned that those positive mu solutions, up to SL2 transformations, remember they can all be mapped to this one basically. What we learn is that those positive mu solutions, when you take back reaction fully into account in Einstein-Maxwell theory, what they will do if you start off Bertozzi-Robinson is they will build for you an asymptotically flat region that's associated with a Horizon-Nordstrom black hole with non-zero deviation from extremality given by this square root here. So that's Anabasis. So let's summarize real quick what's Anabasis. It's back reaction that destroys the ADS2 boundary and builds an asymptotically flat region of extreme and near extreme black holes. All right. I guess a few remarks. It's natural to ask, what about JT gravity? I'm talking in 4D language only, but it's natural to ask what about JT gravity. Well, all of these quantities, of course, make an appearance in the JT formulation of higher dimensional gravity down, in the JT reduction of higher dimensional gravity down to 2D. So the thing I was calling phi actually gets identified with the JT dilaton and satisfies this dilaton equation in JT theory on ADS2. The thing I was calling mu, the SL2 invariant, is an ADM mass of 2D black holes you can define in these 2D theories of gravity. And the thing that many people call nearly ADS2 geometries are precisely the geometries you can make by adding this type of Anabasis perturbation to your exact ADS2, and therefore now having the SL2 broken appropriately such that you're maintaining connection with an exterior region. So this is what you would call nearly ADS2 solution in this context. So it's basically the background, the exact ADS2 thing, plus the Anabasis perturbations. All right. And I guess if you care a lot about horography, you would also want to know what is the dual of doing Anabasis in ADS50 type of language. Well, that's a little trickier. I'm not 100% sure. I mean, the basic intuition is the following. What it is doing is it's following inverse RG flow from the IR to UV along an irrelevant deformation, but in such a way that you don't respect the ADS boundary conditions. That's not something we very often do in ADS50 language for good reasons, but it does happen. In fact, string theory was discovered, holography was discovered this way, right? From string theory going in the opposite direction. It's a hard question if you start from the IR. It's a hard question to go up because you don't know how, what deformation to follow that's solvable. The only example I know where this has been done successfully is for ADS3, not ADS2. There are these TD bar deformations, single trace version of them, which people understand that they start with an ADS3, they follow it, they can solve it, and they produce an asymptotically flat linear dilaton type of solution. So this is an example of how this type of Anabasis or inverse RG flow can work. Now, what it is for ADS2, though, not so clear. I don't fully understand how to think about RG in 2D. Yeah.
Can you say that this is analogous to, you take NS5 brains, you take a near horizon unit, where the solution becomes extreme times the linear dilaton.
Mm-hmm.
So the Anabasis in that case would be to start with this, which has an exact description, and see how we can restore back the one, which retains the space perfectly flat.
That's right. Yeah.
Is this analogous to
Yeah. That's the intuition indeed.
the case I just mentioned? This has been done 15 years ago.
Right. If you know the parent theory, of course. I mean, string theory. Holography was discovered this way. If you know the string theory, you can go down. Yeah, you don't know what's up there, and which deformation you should follow in such a way that it is solvable, etc. And you discover the physics of asymptotically flat. That's difficult. Right. Yeah.
But also, like in the ADS2 case, right? I mean, so for example, there is this example like that you got like a high-dimensional ADS black hole, like for example ADS3, right? So you start like from near ADS2, and then I mean you go reverse the actually flow, I mean you end up like with ADS3 and ADS3.
Right. That's also another setup where this can be understood. I suppose if it's going from asymptotical ADS2 to asymptotical ADS3, that there's more control in there. That's also a good point. Yeah. Yeah.
That's what a little bit of what I think what collaborators did is look at the near horizon of NS5F1, and basically you add the one that you get out of that throat, and you go to the linear relatum of the center.
Right. Yeah. But we want that type of understanding for something that starts with ADS2, and so yeah, that's different from what Kudosov and friends have. There's less control. Okay. I mean, I don't even fully understand what it means to say that you're doing you're adding an irrelevant deformation of, I don't know, conformal quantum mechanics, some CFT1 type thing. Yeah. In one dimension, what does RG mean? This is a tricky question. Okay. Good. So that was analysis. But the main part of my talk is about this accidental symmetry that we discovered. So there's an accidental symmetry, which is, what is an accidental symmetry? We define it as a coordinate transformation which acts on perturbative solutions of the Einstein equation, so solutions to the linearized Einstein equation, around extreme and near extreme horizons. So there are some coordinate transformations which can map various solutions of these linearized Einstein equations around extreme horizons. So let's be a little schematic and describe what these are. So imagine that you have this, which is a schematic for the linearized Einstein equation, which you build out of a background geometry G bar, and you find solutions for the perturbations H. So you want this equation to be satisfied when there's a background, let's say the Bertozzi-Robinson universe, ADS2 cross S2. There are metric perturbations of it. Let's call them H. It could be one of those ABC solutions, the phi thing. And you're trying to solve this equation. Now, do a coordinate transformation. This is a perfectly covariant equation of motion. So if you do an arbitrary coordinate transformation like this for an arbitrary vector field C, you will transform both the background G, that's a tensor, and the perturbation H, that's another tensor, in such a way that for arbitrary lambda and C, this equation is still valid. This is just general covariance. All right, now expand this in lambda. So make a linearized diffeo, so an infinitesimal diffeo. At 0th order, you have this term. At first order, you get two terms. You get a term when you expand H, and you get another term when you expand G. If you start with a solution of this original equation, then this is 0, and therefore the sum of the other two has to be 0. So no matter what diffeo you did, the sum of these two terms always has to be equal to 0 if you are transforming an initial solution. But let's think about what these two terms actually mean. The first term says, hold the perturbation fixed, but do an infinitesimal diffeo on the background. The second term says, do the opposite. Hold the background fixed, but transform the perturbation, transform the solution. The sum of them is always 0, but what if we impose the requirement that we want each of them individually to vanish? So suppose I want to insist that the second term vanishes by itself. What does that mean? That means I want to be able to find a transformation of various perturbative solutions around the same background in such a way that this equation is satisfied. Should there even be such solutions? Should there be diffeos I can do just on the perturbation and get a solution? Well, if you think a little bit about it, you know that there should be at least one type of such diffeos if there are isometries of the background. If the background has isometries, symmetries, then I can act with those isometries, and my background doesn't transform. So the transformed G bar is the same as G0. Well, in that case, this is just the original thing. This is just this, and it has to be 0 by general covariance. So if there are any isometries of the background, this equation has to be satisfied, and it always will be. Now, anything more than that, we call an accidental symmetry. Anything more than that doesn't have a simple explanation like that, and it would need explanation if it exists. So any other solution, any other transformation that you can do, which transforms various solutions H of this linearized Einstein equation, is an accidental symmetry by our definition. So let's run this experiment on the simplest case, where the background is just Bertotti-Robinson. The perturbation is, let's say, one of those mu = 0 solutions, this one. And we're solving the linearized Einstein-Maxwell equations in electrovacuum in spherical symmetry. Well, if you actually solve this equation for all of those vector fields Xi, you find that the solutions take this form. These are all of the solutions for an epsilon of t, which is an arbitrary cubic polynomial of t. So what is there? Well, E0, E1, E1, E plus minus 1, and E0 are the things that give you the SL2 killing vectors of ADS2. So you see here, what we said before, that any killing vectors will have to arise in this exercise, and they do. But there is there's a fourth solution. There is this T cubed mode. It corresponds to this vector field, and so that vector field is an accidental symmetry. It's a non-trivial transformation you can do on a mu = 0 solution and produce another solution of the same linearized Einstein equation. Now you will ask, what does this accidental symmetry do? What does Xi minus 2 do? Well, what it does is it turns on mu. So remember, in the first part of the talk, I told you that if you act with SL2s, mu remains invariant. So those will never change mu. But this one could, and indeed it does. So what the accidental symmetry does is it transforms your mu = 0 solution to a mu positive solution in that case, if you put a coefficient E minus 2 here, which is negative. So what accidental symmetries do, even in this simplest of all contexts, just electrovacuum spherically symmetric, is they allow you to move between SL2 orbits. They enlarge the space of possible mappings among solutions of this linearized Einstein equation to go beyond SL2 and basically explore the entire set of available solutions. All right. Now you might ask, why do they call this Xi minus 2? Because in writing it this way, it's very suggestive that you might expand this epsilon of t into arbitrary polynomials. And so you might ask, what does Xi minus 3, Xi minus 4, etc., what do all of these guys do? Well, these guys produce perturbations that now move off shell. They no longer produce perturbations which will solve the classical linearized Einstein equation. They move off shell, but they have the nice feature that they generate the Virasoro algebra. So if you consider all of the modes like that, with Xi minus 3, minus 4, etc., you will not be satisfying the Einstein equation anymore across the boundary, but you will have off-shell modes which are generated by Virasoro transformations of ADS2. So they are basically asymptotic symmetries. So what we learn here is that the accidental symmetry we found, together with the isometries of the background, neatly fit into the asymptotic symmetries of ADS2, the known asymptotic symmetries of ADS2. Let me make this a little bit more precise in the context of the JT theory of gravity. So suppose now you're doing this 2D theory of gravity, which approximates very well, which describes very well these dynamics in the spherical symmetric sector, at least, of black holes near extremality. What are the large diffeos of ADS2? So in Fefferman-Graham gauge, they are these guys. So you can see here that near the boundary, what this is doing is it's reparameterizing the boundary time. Remember, the boundary is in R equals infinity here in this coordinates. If you apply this large diffeo on the Poincare, let's say, background, you produce this as far as the geometry goes, and you make an original ABC solution transformed to this type of dilaton. Now this is the dilaton of the JT theory, where phi naught, the source, is given by this equation here. So if you transform an original ABC solution via these large diffeos, you make such a phi naught, and such a phi naught trivially satisfies this Schwarzian equation of motion. This is an identity. If I actually plug in this expression here and compute all the derivatives, it will be 0. All right, so there's nothing to solve here. I wouldn't call this even an equation of motion. But these are the large diffeos. Why am I saying that putting the large diffeos on shell is to transform them into accidental symmetries? Well, the reason I'm saying that is because the way to turn this into an equation for f of t, for the large diffeos, is to consider that say you started with an original solution that had phi equals to 2r, so phi naught was constant. You do this large differ, but you pull it back, and you still insist that phi naught after the transformation is still a constant. So this is a new boundary condition. It changes the situation. And what it ensures is that you can still, basically what it ensures is that you can still glue into an asymptotically flat region that is a Reissner-Nordstrom region. So if you insist on that type of requirement, that phi naught, even after the transformation here, has to be constant, well, then you might find solutions that you might find constraints on your differs, on what f of t you can do. And indeed, if you set phi naught constant in this equation, the Schwarzian equation, it turns into an equation for f of t. If you consider only linearized differs, so f of t is t plus epsilon of t, this equation is just these 4 derivatives of epsilon, and it has the 4 solutions that we have already seen, the 3 things that are associated with the SL2 isometries, and the 4th one, which is the accidental symmetry. All right. Now, on to something else. So far, I've been discussing only solutions of the electrovacuum Einstein-Maxwell equations within spherical symmetry. And so the only interesting thing I was finding is, because of Birkhoff's theorem, is this one accidental symmetry xi minus 2, which all it can do is it can add a little bit of energy, just adding a charge to the black hole. Can you have accidental symmetries do something more interesting? Turn on dynamics, turn on propagating degrees of freedom. You can. So the simplest way to do it is to not go away from spherical symmetry, not go away from Reissner-Nordstrom, stay here, but add, say, scalar matter. Add just a Klein-Gordon field that solves this equation here. And the most general solution for this Klein-Gordon field is, a superposition of ingoing and outgoing waves of ADS2. This type of, the most general solution like this, these are now propagating scalar waves, can actually all be generated. So they can all be generated by a diffel, which you can use to act on the vacuum anabasis perturbation. So suppose you start with h of 0, which was just the 2R solution, and you want to act with an accidental symmetry, a diffel, which will turn this solution into a solution that solves this linearized Einstein equation, with the source here being the Klein-Gordon source associated with this scalar field. Well, you can do that. So here's the differ you need to do. So this is an accidental symmetry that will turn on any desired propagating scalar wave on top of ADS2, starting from the vacuum anabasis perturbation. So that makes accidental symmetries much more powerful, and they give them more content than just adding charges, which is what you might have thought about when I advertised them as asymptotic symmetries put on shell. All right, but we wanted to generalize this for the rotating black holes. Those black holes that are out there in the sky, which have a near horizon which is NEC rather than just ADS2 cross S2. And doing that required us to think about it again, because it was hard to do the old way. So we devised a new method. Let me quickly explain the method. So imagine, we will explain it on Reissner-Nordstrom before we apply it on NEC. So imagine that you have the extreme Reissner-Nordstrom, and you have this series that you write in this one parameter frame of coordinate, leading term Bertotti-Robinson. Here is a linear correction of it, and you start with a solution that is a mu equal to 0 solution. It's a mu equal to 0 anabasis solution, so it solves the linearized Einstein equation for Bertotti-Robinson in Poincare coordinate background. Previously, when I said what is an accidental symmetry, I was saying anything that can solve this equation. So any x's that can solve this equation when applied to this H. Now doing that for NEC is kind of difficult. But what's the intuition? I mean, we know that there are non-trivial solutions to this equation basically because both the extremal and the near extremal black hole had the same Bertotti-Robinson as their near horizon approximation. That was really the key evidence that led to a non-trivial solution to this equation. So let's see if we can arrange for that. So suppose now you think again about doing this linearized differ only on the perturbation. So you send H to H plus the derivative of H, and let's say the differ is of size mu. What we learned before is that for the accidental symmetry of interest, psi minus 2, this thing that was produced this way could have been thought as a new perturbation around Bertotti-Robinson, which in a series like that builds not extreme Reissner-Nordstrom anymore, but near extreme Reissner-Nordstrom. So unlike this guy, little h, which built extreme Reissner-Nordstrom, this guy builds near extreme Reissner-Nordstrom. So an idea for a method for finding this psi minus 2 without actually going into solving the Einstein equation is to find a one-parameter family of coordinates that you apply on generic Reissner-Nordstrom in such a way that they can expand in the parameter lambda, but also in the deviation from extremality in mu, and have this type of double series expansion of Reissner-Nordstrom. If you can identify such a coordinate transformation, well, then you will be able to identify psi minus 2. Let's see how. Let's see how you do that in practice, let's say for Reissner-Nordstrom. Starting from the first line, we already showed that this type of series from extreme Reissner-Nordstrom can be produced from this limit. Now, if you have a near extreme Reissner-Nordstrom, let's say of charge to mass ratio of this form, imagine doing a further coordinate transformation, following up that one with this one. So this is now so far an arbitrary coordinate transformation Xi of size kappa squared. If I combine the two, what I mean is that I will do this coordinate transformation on generic Reissner-Nordstrom. And then I will expand in lambda, but also in kappa. So what that produces is this series here. So now I have generic Reissner-Nordstrom, which I have written in this set of coordinates. Kappa is the thing that parameterizes the difference from the deviation from extremality, but I am expanding in kappa as well. And so I have these 4 terms. Now, if kappa was 0, then that means I'm just in this story. I'm doing the expansion of an exactly extreme Reissner-Nordstrom. So obviously, I have this series, and therefore, this little h here is a linear solution around the background Bertotti-Robinson. But notice that in this series, I can also think of setting lambda equal to 0. And then this guy here is also the first correction of an expansion of a nonlinear solution around another nonlinear solution. So that big G here is also necessarily a solution of the linearized Einstein equation around the same Bertotti-Robinson background, and that's for an arbitrary Xi. This big G and this big H, they come with kappa squared, so they depend on Xi. But for an arbitrary Xi, this big G is always a solution. How about this H? Is that a solution around the background G Bertotti-Robinson? Well, not generically, because now this isn't just a linear correction around the background G Bertotti-Robinson. But we can make it. So suppose we do want this to be true. We do want the H perturbation to be a linear solution around Bertotti-Robinson. One way to achieve that, and the only way here really, is to set this big G equal to 0. So now that gives you equations for the diffie of Xi. If you do this, you will make this series look like that. And if you solve the G equal to 0 equations, you will find that the solutions are these. So precisely the accidental symmetry plus the SL2 generators. All right, so let's recap real quick. What do we have? Initially, we have little h, which is a mu equal to 0 anabasis of Bertotti-Robinson. Little h, mu equal to 0 anabasis of Bertotti-Robinson into extreme Reissner-Nordstrom. Now, looking at this line, we have h plus kappa squared big H, a mu positive anabasis, because it's going to build out of Bertotti-Robinson a finite temperature Reissner-Nordstrom black hole. Now, does that look like this, the way we defined accidental symmetries originally? It does, provided I can identify big H with a Lie derivative along this specific psi minus 2. Can you do that? I'm not going to go into the details, but yes, you can. You can produce this little h and this big H in any gauge you wish. If you align the gauges appropriately, then you can make sure that this equation looks exactly as before, with this big H now being the Lie derivative of this psi minus 2, along this psi minus 2 of this little h. So that can also be done. For Reissner-Nordstrom, it's relatively easy. For NEC, it's uglier. But let's see the derivation of psi minus 2 and look at it also for NEC. How much time we have? 10 minutes, right? Yeah, okay. So NEC. Now, NEC is much complicated. This new method was devised to treat it, actually. So here, why is that? Well, because KER is kind of complicated, but here it is in all of its glory. It's a beautiful solution, somewhat more involved, but a very beautiful solution. The extreme KER here is obtained by setting the parameter A to M. So this A measures the angular momentum. So maximal spin is A equals to M, and if you do A equals to M, you have extreme KER. The way to get NEC out of it is to apply to it this coordinate, one parameter family of coordinate transformations and expand in lambda. So then you have an equation like this, extreme care, neck plus the first order correction, H. Again, looking for accidental symmetries by actually solving this linearized Einstein equation like this for C is tricky. Why? Well, because first of all, in metric formalism, there's no gauge invariant quantity. You might have to go to Newman-Penrose formalism. But most importantly, in this equation, it's hard to ensure that the angular dependence separates from the radial dependence. So if you've ever dealt with the linearized Einstein equation around rotating spacetimes, you know all of these difficulties. So let's use the second method. Let's use the second method. And what does that mean? That means consider generic care, which you know. When you know the entire family of asymptotically flat black holes, the nonlinear solutions, you can use method number 2, the new method. So take this care solution, and imagine that it's not exactly extremal. It's just generic care with this charge to angular momentum to mass ratio, and do this coordinate transformation on it. So take this with A over m equal to that. Do this coordinate transformation on it, and expand now again in lambda and kappa. The way to obtain this transformation is again start with this one and follow it up by sending T and R to kappa squared corrected versions of themselves. If you do this, you will produce this type of series starting from the nonlinear solution of care. And so now again, you can ask, are there solutions to this equation G equal to 0? If there are any, then that will be an accidental symmetry. It will produce a new solution that is a linear solution around just neck. And if you do this for care, for neck in this case, you do get, again, a bunch of solutions. What are the bunch of solutions? They are the isometries of neck, which are SL2 cross U1. There's also U1 due to the rotation thing here. But there is yet again a new solution. I'm going to call it psi minus 2 again, and it is written here. So it's basically the same as before, has a d by d phi term here. And again, as before, together with the isometries, with psi 0, 1, and minus 1, they collectively combine very neatly into these vector fields. So once again, if you consider other modes of this, then you are moving off shell, but you might be interested in doing that because these are actually Virasoro generating vectors. They have been previously proposed as asymptotic symmetries of Kerr CFT. Never fully understood, but they have been proposed. And interestingly, there is one interesting difference between the Rice and Nordstrom story and this story. If you want to make sure that what this produces is something like that, but with this big H now, so the lead derivative of the specific psi minus 2, you need to adjust the gauges, as I said before, for both this little h and this big H. But unlike the Rice and Nordstrom case, you would only be able to see this equation arising in a gauge that is singular. So that's curious. It's nothing to worry about, because if you don't go to those singular gauges, all of your perturbations, all of your vector fields are perfectly regular. But if you want to display this equation, you only can do that in singular gauge choices. Okay, that's not the first time it appeared in perturbative problems of neck. It's curious. One might wish to think more about it. All right, so I have a few minutes, so let me summarize real quick. What are accidental symmetries? Accidental symmetries are coordinate transformations which act on perturbative solutions of the linearized Einstein equation around extreme and near extreme black hole horizons. And what they do is they map perturbative solutions amongst themselves. We saw that for the story Bertotti, Robinson, 2, Reisner, Nordstrom, what they do within spherical symmetries, there is one such accidental symmetry. What it does is it turns on deviation from extremality. Start from exactly extreme one, you turn on deviation from extremality. For neck, similarly, this psi minus 2 I just showed for neck is doing a similar thing. It can start with neck plus a perturbation that's going to give exactly extreme care, and it then produce a perturbation that's going to start from neck and produce near extreme care. In both cases, that psi minus 2 combines neatly with the background isometries, the SL2s, into a Virasoro algebra. And in both cases, it can be thought of as a non-shell version of a large diffu, of an asymptotic symmetry of those asymptotically ADS2 solutions. Now, what's more than that is that we saw, even within spherical symmetries, that I can use accidental symmetries beyond this type of addition of charges. But I can use accidental symmetries to turn on dynamics as well, turn on propagating waves. The way we did it for Einstein-Nordstrom is we added scalar waves in spherical symmetry, and we turned them on with certain vector fields. Now, what are we doing now? We're doing the same thing now for gravitational waves of NEC. This calculation for scalar waves of Einstein-Nordstrom is proxy for the axisymmetric gravitational waves of NEC. And so we expect, this is still work in progress, of course, but we still expect that it should be possible to turn on gravitational waves that are axisymmetric around NEC by acting on the Anabasis solutions of NEC with some appropriately chosen diffeomorphism. All right, this is the end, and I'm happy to take questions.
I would like to put this accidental symmetry in something that everybody can understand.
Okay.
Take the isotropic harmonic oscillator in the plane.
Okay.
We know that for the U1 symmetry, there is a hidden symmetry, which is SB2, which you don't see geometrically. So that means I can construct from the creation and annihilation operators of the harmonic of the two sets of the two harmonic oscillators, the generators of this hidden symmetry, and see that they close in SB2. Can you do something analogous here and say the finite dimensional algebra of the symmetry or infinite dimensional symmetry?
Right. So if you allow me to go off shell, we've already closed it into the Virasoro. So if you allow me to go off shell,
Offshell means satisfy the equation.
right. So means don't take only psi minus 2. But so we already showed that psi minus 2 is an accidental symmetry that takes your perturbations and makes them stay on shell, so still solve the Einstein equation. Now, take this psi minus 2 and commute it with the other symmetries, which are the SL2 vectors. You will generate, other vector fields, and the algebra that closes this thing is the Virasoro algebra. So these guys here, for an arbitrary epsilon of t, are the Virasoro algebra. Is the Virasoro algebra. Yeah, what that means is that unless you use psi minus 2, if you use any other Virasoro generator on the perturbations, you will produce things that go off shell, that don't satisfy the Einstein equation. In other words, they still will, of course, produce diffeos in the ADS2 region. But the question is, are those perturbations, which are diffeos of the ADS2 region, therefore trivially solve the Einstein equation, are they gluable onto things that are still solving the Einstein equation outside of ADS2 once you bring in the exterior? That kind of question, the answer to that question is only for the psi minus 2 mode. So they move off shell in that sense. Not in the ADS2 region, but in the full asymptotically flat region, they move off shell. If you stay on shell all the time, then you collapse. Then you have to collapse all of the other ones and keep only the psi minus 2 here. So then your algebra will not close. So the classical solutions of the Einstein equations, their accidental symmetries around this ADS2 cross S2 are just SL2s plus this one.
When you say off, can I elaborate a little bit? When you say off cell, could it be that you generate Ramon fields or something within type 2?
Yeah, when I say off shell, all I mean is basically not solving the classical equations of motion necessary. But you can make those perturbations with Virasoro generators and quantize them.
Even by including Ramon fields?
Yeah, you don't have. No, you don't have.
So on NEC, recently these papers that were trying to look at these fluctuations from the point of view of the path intervals to compute the contribution that in that context there would be off-shell fluctuations along the nodes, and basically there are the zero modes that enter into that path interval with these diffeos that you're describing here.
You're talking about calculations, one-loop calculations, let's say for log t corrections, that type of thing? Okay.
So in that case, it's you're also looking at perturbations, but they're not on-shell perturbations.
Right.
Because you're doing
Yeah.
path intervals.
Hmm?
So there was this
interesting.
And the way
Yeah.
that you're setting it up, it could be more exhaustive and saying,
Mm.
these are all the fluctuations that
Right.
contribute. So the SL2 ones are not typical to see on NEC, but they were the
Right.
axisymmetric ones, the ones that come from the U1 that
Yeah.
are problematic to construct.
Right. So let's recap first. The first comment that Alejandra made is when you're considering zero modes in this type of one loop calculation, you have to consider this psi minus 2 thing because you have to do this around near extremal backgrounds. Basically, you can't do it exactly on the extremal background. So that's you have to do that.
First discover them by doing them on the external
Right.
background, and then you correct them by adding them.
Good. So that's the story even for Eisen Nordstrom. You do that over there as well. Now for NEC, it's more interesting, and I think the difficulties you're referring to have probably something to do with the following. So if you were to find all of the accidental symmetries of this thing around NEC, even on shell, you wouldn't land on just the psi minus 2 thing because here we're in vacuum, but even within axisymmetry, unlike the spherical symmetry case, there are also the NEC waves. So there is a lot more than just psi minus 2 you have to take care of. So when you're going to consider zero modes around NEC, zero modes around NEC, even the axisymmetric ones, doesn't contain only psi minus 2 things, which add a little bit of energy. It also contains all of the NECs, all of the waves of NEC, the propagating waves of NEC. So it's more similar to this stuff, all of the scalar waves I put on top of the Reisen-Nordstrom background. So I would have this type of accidental symmetries to worry about as well in the case of NEC. So this is the thing we're trying to work out right now, actually, basically. What's the analog of these guys for the NEC waves?
Sorry, are you saying that those will turn on temperature as well? No.
Not necessarily. But what I'm saying is that they are necessarily there because this equation necessarily has not just the thing that turns on temperature, but also the waves. That wasn't true for Reisen-Nordstrom, and it is true here. So those modes are there.
I can control from boundary conditions, right? I can just say I'm looking at the conditions that does turn on temperature. But okay, maybe
You could, but I don't know if that's what you want to do. Okay. Okay. All right. Thank you.
Thank you. Thanks for the introduction. And also thank you to the organizers for the very nice meeting and the invitation. Very happy to be back in Athens. So indeed, I'll talk about integrable structures in twistor-formed ADS-CFT, which is based on work, almost all of it with my collaborator Ricardo Borsato in Santiago de Compostela. But I also mention briefly a recent work that I did with Niranjan Kamath, the master student at ETH. And so the motivation of this work is coming basically from studying deformations of ADS-CFT and use integrability to do that. Now you can take a very simple advertisement for that, which is just looking and studying at models of QFT and quantum gravity where we have less neutral symmetries, but we do have integrability, meaning that we have some infinite set of hidden type of symmetries which highly constrain your dynamics, and you can still make predictions on these type of models. In particular, you have sort of two ways of using integrability. First, there is what is called lax integrability that we typically use to study properties semi-classically, which I will mention. And then the second one is based on S-matrix integrability, where we typically use that to go to the exact quantum regime. Now I will focus on an exceptional undeformed case of ADS-CFT that we all know very well. So the duality between ADS5 and CFT4 at large n, where we have this nice triangle picture that is not super clear on the slides, but so sort of we have these three type of corners, where on one corner we have our string theory, so some strings propagating in this highly symmetrical ADS5S5 space-time that we know to be dual to NS4 super-Yang-Mills gauge theory. And the nice integrability story that we have here is that there is some underlying integrable quantum system formulated through a PSU2,2/4 spin chain. Now, this setup is extremely symmetric. So we have maximal supersymmetry. We have this PSU2,2/4. There's also a CFT in here. And there is this underlying integrability. So the question that I want to ask is, can we deform these particular symmetries but keep integrability? And the tool that I have been focusing on in recent years is to do that with so-called Yang-Baxter deformations. The reason for that is that they sort of have a modification of this triangle, which is conjectured to be through what is called Drinfeld twists. I'll very briefly say a little bit of what that is, but basically it's just a nice algebraic way of deforming the integrable structures. I will focus on the string corner here, where the picture that we have in mind is that the string is now propagating in some deformed 10-dimensional space with deformed through an object that we will call the R matrix. And then the conjecture is sort of that this should be related to a non-commutative, in general, a non-commutative gauge theory, where the product between the fields is also sort of Drinfeld twisted. It becomes non-commutative through similarly a Drinfeld twist. And underlying to that, we should have some Drinfeld twisted spin chain, where the result of Drinfeld twisting basically becomes that the spin chain is not closed anymore, but if you go around it, you pick up some twist, exactly a Drinfeld twist. And so I want to ask in this talk how we can apply or even extend the known ADS-CFT integrability methods that have been working very well in the usual ADS5 case. And in particular, I want to focus on the modification of the scattering problem on the worldsheet, so in this corner, in the string theory corner. Good, but I also mention a bit of lax integrability because there everything is working very nicely, and then I will focus on this S-matrix integrability. All right, so before I do that, I will tell you what are Yang-Baxter deformations. So they are particular worldsheet type of sigma models So they are deformations of two-dimensional sigma models with some isometry Lie group or Lie supergroup G. So in the case of undeformed ADS5S5, G is PSU 2,2/4. And then we have a nice two-dimensional action, a worldsheet action that takes this form. The particular details are now not entirely important, but just to show you that we have an actual action that you can study. We have a similar notation as Ben previously. So basically the fields here are these objects G that are mapped from the worldsheet to this supergroup. So they are elements, so they are supergroup elements. And I can parameterize them through coordinates X, where the number of coordinates is, of course, the dimension of this supergroup. And then we have this current J, which is the Maruc-Cartan form constructed out of this group element. Now, the deformation is controlled by a parameter that I call eta, as well as an operator that is this R matrix that I mentioned previously. So it's an R operator acting on the Lie algebra of PSU 2,2/4, and it has to satisfy a number of algebraic constraints. So the first constraint here is what we call the classical Yang-Baxter equation. It's some quadratic constraint for R. Then it also has to be anti-symmetric with respect to the trace of the algebra. And then in some adjoint representation, I can look at the R matrix related to the operator. And when I contract it with the structure constants of this Lie algebra, I have to get 0. That's what we call the unimodularity conditions. Again, details are not important, but basically when we have these three conditions that are solved, you're guaranteed that the deformed worldsheet model will preserve integrability, and it will also, the target space geometry that you will get from this worldsheet will be a solution of type 2p supergravity. So there are sort of ideal models to look at deformations of ADS-CFT with integrability. Okay, and then I just very briefly want to, of course, we can also just go and look at this action in detail in terms of stuff that you're familiar with. So I could look at the bosonic truncation of this action and expand in these coordinates X. And then we will have some target space metric G and some target space metric B field B that will be deformed by this particular relation, and in particular it depends on this R matrix again. And then we can also have some deformed Ramon-Ramon fluxes, etc. Yeah. Yes, yes, absolutely. Yeah. Yeah, I mean, there will be some supersymmetry in some cases. In most cases, there will be zero supersymmetry. I will mention one particular case later. But we have integrability, yeah. That's interesting. I think so. I think that's possible. Yeah. I mean, we worked on that for other deformations. Now you can see that indeed these boundary conditions. Well, actually, the boundary conditions. No, they don't. They don't get to form this. It's a bit of more of a global property. Yeah. 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 So there, in some cases, we saw that the D-brane, the geometry would get deformed, like how it really looks, but the topology is the same, so sort of the boundary conditions are the same. But okay, we can discuss it at another point. Good. So we have these fields, and they also have type 2b supergravity. And in particular, if I just care about the worldsheet theory, I will have interactions that are deformed, and so I will have a deformed scattering problem, right? Good. Now, I would just want to quickly mention that there are actually a bunch of solutions to these three equations, and we have classified them for PSU 2,2/4 under certain conditions. So there's a huge family, I can say, and some of them are, some of these cases are probably well known to you. So one of the most well-known cases is the Lunin-Maldacena background, which is a particular Yang-Baxter model. Then we also have Schrödinger spacetimes, as well as the Hashimoto-Izaki-Maldacena-Russo background, which all have been studied quite a lot. A second thing I want to mention is that also solutions to these equations are in one-to-one correspondence with these Drinfeld twists that I mentioned, which are connected to the identity. And so the Drinfeld twist I will denote with this curly f. And to first order in deformation parameter eta, it is governed by this object that satisfies these conditions as well. And it satisfies a bunch of other due to these conditions. There's actually a nice algebraic modification of all the integrability. I will not go into that much further, but I can give you more information if you want after the talk. Okay, good. So now let me just go through three sort of main classes that I will be referencing to throughout the talk. Which are distinguished by the subalgebra of the image of this R operator. They are that subalgebra is minimally two-dimensional due to this anti-symmetry property, and I will denote the span of it. I will denote the generators of it by T1 and T2, and then we can sort of think of three classes. We have either this image of R being a abelian class, and the generators Ti diagonalizable generators, so they are some type of Cartan generators. This is known to correspond to what is called diagonal TST, for those that don't know that. So TST is just some type of worldsheet transformations that you can do involving T-dualities and shifts. And in fact, the Lunin-Maldacena background is a type of diagonal TST transformation. Then we have these other classes. So we have also the image of R abelian, but one of the two generators is not a diagonalizable generator. It's not a Cartan generator. I mean, for lack of name, I will just call it non-diagonal TST. And the Schrödinger spacetime and the Hashimoto Itaki Maldacena Russo, they are examples of non-diagonal TST. And then finally, the third class that I will focus on later is where you do sort of a more of a radical change, where the image of R is a non-abelian subalgebra. It's some SL2R subalgebra of PSU 2,2/4, where one of the generators is a Cartan of SL2R and the other one is a raising operator. And these type of deformations are very much unexplored and are called Jordanian deformations, and they sit sort of in this larger class. Now let me just mention in these three cases, there are some known associated Drinfeld twists to that, and in the Jordanian case, the Drinfeld twist should be diagonalizable. Then we have this diagonal TST where the Drinfeld twist should be diagonalizable, and then for the non-diagonal TST, it should not be. Okay, and then before going to the actual integrability program, let me just mention what we know about the deformations of NS4 Super-Yang-Mills. So there we have a bunch of possible marginal deformations. One of them, which is very well known, is the beta deformation. And these you can obtain when we take abelian generators, which are elements of the SO6 subalgebra. So they are deforming at the string side, they are deforming the sphere. But they are leaving ADS5 intact, and so they will give a marginal deformation of NS4. And this is, of course, connected to the Lunin-Maldacena case as well. Then you can also have non-commutative deformations, which happens when one of the generators have a lag in SO2,4, so you will be deforming ADS5, and so it will not be a marginal deformation anymore. But you will introduce some non-commutativity in the space-time of NS4 Super-Yang-Mills. And then finally, these generators in SL2R, these corresponding to Jordanian, we really don't know what they are at the Super-Yang-Mills site. Okay, good. Are there any general questions? All right. So then let me go to the integrability program of these models. So first, I will discuss a bit about lax integrability. I'll try to be brief. So let me just define for you what that means. So lax integrability of the sigma model basically means that the equations of motion that you construct from the field G can be represented in terms of a one-parameter family of flat connections that we call a lax connection. And I will denote it by this curly L. They depend on the fields and as also on this arbitrary parameter Z. Which we call a spectral parameter. And I think in Ben's talk, there was a zeta in his case. And so these objects, they are flat for every value of Z. And if you have such a structure, the result is, what you can do is that you can look at the eigenvalues of the Laxus monodromy matrix. So I denote it by MZ. The monodromy matrix is this object here. And if you look at the eigenvalues, you will find that they are conserved for every value of the spectral parameter. So I could, for example, expand around specific points in the complex plane Z star, and I will find in the expansion each coefficient Q here will give me a conserved charge, so I will get infinite tower of conserved charges. They will typically be non-local, but sometimes you'll also find some nice local neuter charges among them. Now, the nice thing about these Yang-Baxter models is that they not only have one lax connection, but in a certain sense they have two lax connections. And this is related to the fact that those models actually, if you look at the deformed theory, you can realize that they are related to the undeformed theory by some canonical transformation, which is non-local. So in the bulk, it's sort of the same type of theory, but globally there is something strange happening. So basically, you can sort of have two pictures. So we have this traditional picture here, where we have a nice periodic closed string propagating in some deformed target space, where the deformation is controlled by eta r. And then with this non-local canonical transformation, you have a second picture where the string is propagating in an undeformed space, but it receives some twisted boundary conditions. So the string itself, if you go around, it receives a twist. So that means that basically we either have, on this side, we have fields that are just periodic, and they behave in this deformed, they propagate in this deformed space. So their equations of motion will change, and therefore the lax connection will change, and it changes in this particular way, again, depending on eta r. But in the second case, the equations of motion will not, the bulk equations of motion will not change, but the fields pick up some twist if I go around them. And yeah, so therefore I will have locally, I will have an undeformed lax connection, but globally, I will have a twist in the boundary conditions. So you mean for it's for all Yang-Baxter models? So for all Yang-Baxter models that satisfy these conditions, In fact, actually, only the first two, but. No, then probably no. Yeah, so most of the other non-integrable deformations don't have this type of behavior. They are not canonical transformations. They really change the Poisson bracket. Yeah. Okay. So good. I was talking about the two laxes, which are local things. Then globally, of course, the monodromy matrix is a global object, and that will receive a contribution from these twisted boundary conditions. So on one side, we have the monodromy matrix constructed out of the deformed lax, and on the other hand, the monodromy matrix M tilde constructed out of the undeformed lax, but with this twist present as well. And this object, we showed that it's a local and conserved quantity, and I will refer to it as a twist charge. Now, one small observation I will come back to in a moment is that there are not really any points in the complex plane where the deformed monodromy matrix will have some nice local neuter charges, but in the twisted picture there will be points where we can find some local charges. But before going into that, I want to make a small other observation, which is that the deformed monodromy matrix, in a certain sense, can be seen as being Drinfeld twisted. So you can massage this type of object and the correspondence between these two pictures. First of all, you will see that the deformed monodromy matrix is spectrally equivalent to the undeformed twisted monodromy matrix. And secondly, you will also find that it's related to the truly undeformed theory, so undeformed but periodic boundary conditions, with this object F that is similar to, has the same structure as a Drinfeld twist. And that's why we say that we expect these type of models to have an underlying Drinfeld twisted symmetry. Also by analogy, what we know from spin chains, where the monatomy matrix is constructed out of products of a quantum R matrix. And if you Drinfeld twist such an R matrix, then you also get this type of behavior. And we also found that to match with what is known for Drinfeld twisted spin chains. So we have typically we have two families of Drinfeld twists. One is an abelian Drinfeld twist, which is of this form, and the other one is a Jordanian Drinfeld twist. And then if you compare these objects, you will see that it sort of matches with the boundary conditions of the string theory as well. Okay, so that just to keep in mind that we have Drinfeld twisted symmetry, which also, was there a question? Yeah. So it also kind of, so the picture is very vague now, but it also kind of nicely fits in this triangle where the string also gets this type of Drinfeld twist, and everything in the corner is basically Drinfeld twisted. Okay, the second observation was about these local charges. Basically, as I said, we can only find local charges in the eigenvalues of the twisted monatomy matrix. And therefore, you can only use a twisted picture up to some other assumptions to study what is called the spectral curve methods that people typically use to calculate semi-classical quantities, corrections to the spectrum of some classical string background solution. So you could do this type of method. You can calculate the energy, the one loop shift, the corrections to that energy, and you will find that it all depends on eta. And we've been able to do that in all cases of Yang-Baxter models, also the Jordanian ones in particular. So it sort of works quite nicely. And in particular, it gives you sort of the first initial ADS-CFT data on the string theory side, if you want. So it gives you the first data for the spectrum at large n, at large lambda, 12th coupling, and at large charges. So if you want to make predictions, one can use that. Okay, so basically that is all that you can do with lax integrability. So we have equations of motion represented by flat lax. You can look at the classical symmetry. Here we saw that was Drinfeld twisted. And you can also use these spectral curve methods to calculate semi-classical corrections. So what about this going deeper and go to the quantum regime with S-matrix integrability? So for that, let me first define for you what is S-matrix integrability. So it's, it depends. But for me, the definition, or at least the traditional lore, is that we have elastic scattering. So S-matrix integrable scattering is elastic scattering, meaning that you have end-to-end processes. So you don't have any particle production or you don't have any particle annihilation. And secondly is that you have also factorized scattering. So you have this typical picture here where we have a 3-to-3 scattering process that should be factorized in 3 2-to-2 processes, of which the order doesn't matter. And the fact that the order doesn't matter is captured by the famous Yang-Baxter equation. Now, these are, of course, major constraints on your scattering theory, and they come from basically all these hidden infinite symmetries that we have, and in particular, an infinite set of commuting higher spin local charges. Good. And now, based on this Drinfeld twisted symmetry observation that we had earlier, as well as analogy with what we know from spin chains, where the quantum R matrix should sort of be related to an S matrix, the question I want to ask now is, like, if I have a Drinfeld twisted symmetry, then does the actual S matrix of the worldsheet also get this type of Drinfeld twisting? Now, this is a conjecture that basically dates back to Van Tongeren in 2015. He also proved that with Zimmermann for these diagonal TST cases in 21. But going beyond diagonal TST poses a lot of problems. And so this is something that I want to address. And the first thing that we could do is to test it at tree level. And in particular, we will test it in this deformed picture where we have these deformed interactions and scattering. Okay, good. So I will in particular focus on a certain Jordanian deformation that I've studied with Ricardo a few times, and in particular, it's a nice one because these spectral curve methods are working quite well for them. And it's a certain set of generators that you can take in PSU 2,2/4, where we have this Cartan of SL2R that is related to the dilatation operator and a sort of boosted dilatation operator and J03. And then this raising operator, which is related to momenta generators in this way. So there are just some particular generators in SO2,4. So we will have certain deformed interactions. I will not bore you with how they actually look like in this case, but the main point is that we will have some reduced Noether symmetries. So basically what happens for this case in SO2,4 is that we will have some 5-dimensional algebra generated by these generators. So normally you have 15 generators, now we have 5, and it's basically an SL2R plus 2 central elements algebra. And then also the sphere gets some deformation, and we'll be left with 12 supercharges. Now, importantly, in this deformed SO2, in the reduced SO2,4, there will only be one time-like generator, which is this particular combination of the momenta and the case. In some JIJ, so in some, how do you call this? JIJ basis of SO2,4, so where the I and a J go from 0 to 5, you can represent it in this way. Okay, so and a slight comment also here that I wanted to make was that in the undeformed case, you actually have a family of possible time-like generators. Also, this one will be one time-like generator there. But what we can do is to use the SO2,4 symmetry and conjugations in particular to bring this type of time-like generator to a simpler time-like generator. I will not go into much more, I will not say much more about it, but it's this one which is typically called a BMN time generator for certain reasons. But the point is that these type of symmetries, the full SO2,4 is absent in our deformed case, so we cannot do this type of rotation. Okay, so now if I want to look at the scattering of this theory, I will have to ask, how should I quantize it? And we know that for that, we need to identify the physical phase space and solve all our constraints, also in the undeformed case. So it's some Green-Schwarz type of formulation. And basically, the only thing that you can do is light congauge. For that, we will fix all the gauge symmetries and solve the Virasoro constraints of the worldsheet gauge symmetries. Now, in ADS cross-sphere spaces, what we typically do is we take some time coordinates t that you identify with worldsheet time, and you have some conjugate momenta to an angle in the sphere that you also fix to some value, and you don't consider any fluctuations on top of that. And then you solve the Virasoro constraints for the angle and the conjugate momenta to t. So ultimately, you end up with just d-2 degrees of freedom that are called the transverse coordinates x mu and the conjugate momenta p mu. And they are governed by some very complicated Hamiltonian that is non-Lorentz and non-linear. So it's hard to study the quantization of this theory. And basically, the only thing that you can really do at this point is to go perturbative and do perturbative calculations. So what you do typically is you pick some very simple solution of your string, so some point-like string typically, and you consider semi-classical corrections on top of that. Then it's a very well-known procedure to just decompactify your worldsheet and scale your coordinates in such a way that you can have a nice perturbative expansion in the excitations and a scattering problem that is well defined. So you do that on your complicated Hamiltonian, and you will find like a quadratic part a free quadratic part that will define the propagators for you, and then some higher parts that define the interactions and ultimately the perturbative S matrix. And this is a never-ending, well, it just continues this series. Okay, so now the question is which type of gauge should I pick in my Jordanian case? Now in the undeformed model, as I said, we have this sort of BMN type time-like generator. And it's nice because if you do the gauge fixing on top of that, you will find that the residual symmetries after the gauge fixing will have a nice action on your transverse coordinates. So what happens is you identify the coordinates associated to this generator with the time. The generator will be interpreted sort of as a worldsheet Hamiltonian. And the symmetries that are left are then those that commute with this generator. And there will be some SO4 nice compact algebra that acts very nicely on the transverse coordinates. This I will call the BMN gauge, and it's also good for diagonal TST models. Basically, everything goes through for the diagonal TST, but in the other cases, you will not be able to take this particular gauge. So in the Jordanian case, this type of generator is actually not in the Noether symmetry algebra, and you're sort of forced to take this other type of generator, and we will call this an inequivalent light cone gauge. You will see that the symmetries, they become sort of non-compact, and they act quite strangely on the transverse coordinates. And I will call this the J gauge. Now, one of the key points is that an S matrix is, of course, a gauge-dependent object. So it's describing the scattering of your asymptotic states, and your asymptotic states are defined of how you pick your gauge. If I change the gauge, it's normal that the S matrix will also transform. And it will do that in some way that also has a sort of Drinfeld twisted flavor to it. Now, I will not go into more details, but basically it's just sort of a gauge transformation of the S matrix. And if you would calculate, of course, a spectrum, then you will find that it's invariant. So the physical quantities will be invariant. But the thing is that deformations such as the Jordanian case, you can only do in specific type of gauges. So we have this sort of S matrix integrability description that depends on the gauge. And on certain points we have, for example, the BMN gauge, and I can do a diagonal TST on that. And on another point I have the J gauge, and I can do the Jordanian deformation. And you have sort of this web of possibilities. Of course, on the physical side, on the theory, the physical theory, you know, that doesn't depend on this orange line, on this gauge transformations. So now this sort of refines the conjecture for the S matrix deformation, where we will now have sort of a Drinfeld twisted S matrix in this J gauge. And the question then is now, let's study it at tree level. So we go in this J gauge and we obtain the perturbative Hamiltonian. It's easy to do. And we will have to define the dispersion. Well, we have to find the dispersion relations, which we get from the quadratic part. You go to some annihilation and creation operators, you diagonalize it, and you get the dispersion relations. And you will get this nasty set of dispersion relations. So we have two excitations in ADS, W plus and W minus, which are these nasty nested square root things that depend on the deformation parameter. Then we have two of them that are nice and Klein-Gordon, but with some deformed masses, W3 and W4. And then we have four excitations. We will have four excitations in the sphere, which are just normal and undeformed. Now, two small observations is that one is that this W minus excitation is a gapless excitation. So if I take the momenta to be 0, you can do a little exercise, and you will find that W minus will be 0. Then the second thing is that these dispersion relations are not relativistic, so you cannot do any type of Klein-Gordon type of rules that you're used to for the scattering problem, and in particular for solving the kinematics. So it's just some complicated thing. But okay, then you can go and check the scattering, and in particular compute the T matrix. So you'll find for this particular model that you will have a cubic Hamiltonian already immediately. And this sort of a cubic Hamiltonian tells you that we have a 3-point vertex. So possibly you might have like 1 to 2 processes or inelastic processes. So the first thing you could do is like, well, this is annoying, and can I remove it? Are there ways to remove it? So it could be that you chose some bad coordinates and you need to do some field redefinitions. you could also use some canonical transformations of your model, etc., and just spend a lot of time trying to get rid of this thing. But ultimately, the T matrix that you compute from it should not depend on these filter definitions or canonical transformations. So if this cubic Hamiltonian would be removable, then the T matrix computed from it will be 0. So let's not waste time and just compute it. So then you also, it's not so clear, but you also go to oscillators and you solve energy momentum constraints, etc. And the result is a bit, let's say, sad in a way. So we will find that there are many processes that are forbidden kinematically. There will also be many that are 0 after you solve energy momentum constraints. But we will have 3 processes that are contributing with 3-point vertices. So we have one where the vacuum goes into 3 gapless particles, so and it actually diverges, so this could just be an artifact of perturbation theory. But then we have also 2 creation processes that start at the linear order in eta. And one of them involves the gapless particle, but it's at non-zero momenta. So it has some fixed energy. And so this is telling you, at least at 3 level, that the scattering is inelastic. And it's violating already the first axiom of S-matrix integrability. And then, yeah, you cannot see it, but here are the explicit formulas. So that's not nice. So we had this nice picture of lax integrability where everything was working. But then going to S-matrix, which is a huge program to eventually go to the exact spectrum, we sort of already get stuck at 3 level. So it poses a question mark here. So yeah, let me by this then conclude. I still have a lot of time actually, no? Okay, well, anyway, good, many time for many questions. I wanted to test this sort of Drinford twisted S-matrix object. And the take-home message is basically that, yeah, lax integrability is working very well for all possible type of Yang-Baxter models. But to reconcile it with S-matrix integrability is really unclear. So is it S-matrix integrable? How can it still be S-matrix integrable? Because I do believe that it should be. What is the problem, basically? And this Jordanian case, at least to my knowledge, it seems to be the first example that highlights this unclear relation and challenges the traditional lore. It also opens up many questions. Some of them are under investigation, but of course I would be very happy if somebody would dive into this because it's quite fun to challenge traditional lore. And so one of them, well, let's see. So we have, first of all, maybe there's other ways or other notions of defining integrable scattering and getting factorization. So one highlight, ray of hope, let's say, is that which I didn't mention, is that on the what is called level matching condition, so some type of Virasoro constraint that you still have to impose on your asymptotic states, you will find that there are no particle production processes. Now, typically you want to violate level matching in S-matrix integrability, but maybe it allows you to define a sort of other notion of integrable scattering. Then the second thing is also maybe you just did a bad gauge fixing. We studied all possible types of inequivalent light cone gauge fixings with a lot of people here in the room, and it's not clear how that could be useful to take another type of gauge. We're really sort of forced to take this specific one, but we could imagine to do some non-local canonical transformations to, for example, these twisted variables that I discussed in the middle of the talk, which we didn't consider in our work. Then one could also ask the question of maybe we can just directly take this Drinford twisted S-matrix and go to the classical level to learn about what's going wrong at the tree level. And for that, you sort of need to know how the action of these generators are on the asymptotic states. which is also quite non-clear because they're acting in a quite strange way. Finally, you could just maybe just close your eyes and look at the Bethe equations that are obtained from this weird S matrix, and maybe things cancel out. Yeah, but that's a bit vague. So ultimately, just highlighting some open things in having a full understanding of this Drinfeld twisted ADS-CFT picture. There are also many other questions that we have in these different corners. So what would it be to Jordanian Drinfeld twist, in particular the spin chain? Can you get a Jordanian Drinfeld twisted non-commutative action? That's also a big open question. And so yeah, I hope that you're convinced of the many nice things that are still to be done here. So with that, thank you. Yeah, so we sort of wanted to test the S matrix directly to see if it would solve the Yang-Baxter equation, but we already got stuck on this inelastic scattering from the beginning. Then you could also just, as I said, sort of here, you could just take this Drinfeld twisted S matrix, but you need to know how those generators are acting on the undeformed states, like on the undeformed S matrix. And that is also not clear because they have some nonlinear action, and we really don't know how the Hilbert space is changing, how the generators are acting on the Hilbert space. Yeah, maybe we can. So I'm not sure what you mean. But maybe you can. Yeah. What is true is that this Drinfeld. Well, now you cannot see it at all. But this Drinfeld twist here, it is compatible with like usual Yang-Baxter, like just pure algebraically. It is compatible with the usual algebraic. Yang-Baxter equation. So it should still you should still have this Jordanian Drinfeld twisted R matrix does satisfy Yang-Baxter. That's definitely still true. But what it means on the physical particles of the string worldsheet, that's not clear. So, yeah. So E raising and F lowering. I don't think it's a solution to these conditions that I showed you. Okay, a Drinfeld twist with this type of structure. Okay. Oh, that's interesting. I didn't know that. Okay, good. Yeah, yeah. No.
There was this work of Napi in 1979 who considered what is called pseudo-chiral model, where there is basically, let's say, for SP2 three bosons, and they interact via a term like phi1, del phi2, del phi3, cubic.
Mm-hmm.
So this model is supposed to be also integral because it has very classical equations for motion, Yankee identity as related to Yang. And then Napi computed a closed particle production.
Yeah, but
Against the law. At the time, I guess people were not thinking of integrability too much, etc. He just did the computation saying that it's inequivalent to PCM.
mm-hmm.
So what is the here you also have some cubic interaction.
Yeah, but well, Ben definitely knows the answer. But if I remember correctly, she just gets a cubic Hamiltonian, but she's not like going to the T matrix. And I believe
Not at the time, but she computed the particle production. Not at 3 level. I think she did some good computation.
okay, yeah. But isn't then there's work that like sort of regulate that as well, and it's possible to regulate these type of things.
Okay, first of all,
So that we didn't even like start to compute. So let me just say that it's already quite hard to get this the 3-point for the 3-point T matrix elements. Yeah, and for that we had to like work in expansions in eta and stuff because these dispersion relations are so nasty. But so like you cannot, in principle, you cannot really think of factorized scattering if you have inelastic scattering. So why would you go there? Yeah. It's, I mean, as I said, like I do think there is a notion of still getting integrability, and we just don't really know how. But yeah, so probably the problem is with gauge fixing somehow, but it's really unclear because prior to gauge fixing, you do have all these infinite symmetries. You have also infinite local charges and stuff like that. One could think of like maybe they get lost after gauge fixing. Also, that is also unlikely, but still, like, yeah.
So the particles that participate in this cubic vertex, are they massless or some masses and?
So all of them are massive. There's one involving the gapless particle, but it sets non-zero momenta, so it does have energy.
So you can satisfy the kinematic constraint.
Yeah, which is because you have this weird dispersion relation. Yeah, it's a puzzle, but yeah. Mhm. Oh, I don't see how, but yeah. Yeah, maybe, but yeah, I wouldn't try to. I'm not convinced, but maybe. Yeah.
So we finished today's session. So we have the room like until 5 technically. So it's officially a discussion session. So you can just hang out or just do sightseeing or whatever. Yeah.